Gonna finish up our thermochemistry chapter. Okay, we left off here. Um, okay, we left off here at defining this function called enthalpy. So we need to think about why we had to define this function. So we're going to talk about the first law of thermodynamics. We're going to define enthalpy, explain its classifications as a state function. We're going to write balanced thermochemical equations. We're going to calculate enthalpy changes for various reactions. And then we're going to talk about Hess's law and how we can use that to relate enthalpy changes for different reactions. Okay, so thermochemistry is a branch of chemical thermodynamics. So we've already talked for a half hour about thermochemistry. It's the science that deals with relationships between heat, work, and other forms of energy. So heat and work technically aren't forms of energy, they're ways to move energy. And so when you think about it, the two ways to move energy is to allow heat to flow in or out of a system or do work on or by a system. And the energy that's contained in a system is either potential or kinetic energy. So substances act as reservoirs of energy, meaning that energy can be added to them or removed from them. Energy stored in a substance when the kinetic energy of its atoms or molecules is raised. Also true, you can store energy by changing the potential energy. So for example, we talked about if I pick something up against gravity, I haven't increased its kinetic energy, but I've increased its potential energy. So the total energy of all the total of all possible kinds of energy present in a substance is called the internal energy, and we give it a U. Some books give it an E. The relationship between the change in that internal energy and the amount of heat or work that we see coming in or out of the system is summarized by this first law of thermodynamics, which essentially says that energy is conserved. So if the internal energy of something changes, you have to be able to measure where it went. So heat had to flow in or out, work had to be done on or by the system in order for its internal energy to change. So energy can be transported into a system, resulting in an increase in internal energy. So if the system absorbs heat from the surrounding, it has a positive Q, or the surroundings do work on the system, then it will have a positive work. So that will make it so that delta U is a positive number if delta or if Q or W are positive. So energy can also be transferred out of a system, resulting in a decrease in internal energy. And that would be true if heat flows out and you have negative Q, or the system does work. If the system does work on the surroundings, it's using its internal energy to do that. And so it's a negative work. So this is just a visual of that. You have the system in the middle, you have the surroundings outside, and you can either have a delta U that's less than 0 or greater than 0. And it simply depends on the relative amount of heat flowing in or out and the relative amount of, the relative amount of heat and work being done. So they can both either be coming in or going out. So a type of work called expansion work or pressure volume work occurs when a system pushes back the surroundings against a restraining pressure and the surroundings compress the system. So you want to think about this really as how we use the energy in our gasoline in our car, for example. When we burn gasoline in our car, we increase the volume and that process. And so it pushes up a piston, which then allows that piston's doing work on the surrounding to be converted into the work of turning the wheels on the car. So if you consider that internal combustion energy, the system is the gasoline and the oxygen. The surroundings is the rest of the universe, including the engine in your car. The reaction's exothermic, so heat's given off, and it's a negative Q. The reaction pushes the piston out, so work is done on the surroundings. And so Q plus W, the internal of the energy of the system, decreases. It's a negative value. Work, internal energy, is an example of a state function. And so the value of a state function depends on the state that a system is in and not how that state is reached. So they always give the example in Gen Chem books because it's such a visual one of your altitude. So if you go to the top of Pikes Peak, altitude is a state function. It doesn't matter how you got to the top of Pikes Peak, you'll have the same altitude, but it could take you a different amount of work. You could take a helicopter to the top, you could hike to the top, you could hike around and round to the top. So heat and work are not state functions, but altitude is. So if you stand on the summit of Mount Kilimanjaro, you're at an altitude of 5,895 meters. Doesn't matter how you got there, you're going to have that same altitude. So altitude's a state function, and so is internal energy. That's just a picture. So enthalpy is defined as a sum of a system's internal energy and the product of its pressure and volume. And internal energy, pressure, and volume are all state functions. Therefore, enthalpy is a state function. And that seems like it doesn't matter, but it's going to be super important here in a second. So enthalpy values for specific substances can't be measured directly. You can't know the total internal energy, pressure, and volume of a system, but you can know how much it changes with a chemical process. So we can measure a delta H. We can't measure an H. So if you look at a delta H, and if we say the process happens at a constant pressure, then a constant pressure, the change in P times V is only a result of V changing because P is constant. So a change in enthalpy at constant pressure would be equal to a change in internal energy plus P times delta V. So the product P times delta V is a measure of work. So by definition, P times delta V is negative of work. So at constant pressure, Q equals QP. And we can see that because delta U equals QP plus work. And if you substitute into the enthalpy change equation, we get delta H equals delta U, which is QP plus work. So QP meaning the heat that's transferred at constant pressure plus work is delta U minus W, because we just said that P delta V is equal to minus work. And so if you have plus work minus work, if you're at constant pressure, that means delta H is just a measure of how much heat is transferred at that constant pressure. So we usually do reactions at constant pressure in chemistry. That's why we've created the function enthalpy, so that we know if we're measuring Q, which isn't necessarily a state function, but if we measure it at constant pressure, it's equal to delta H, which is a state function. So that will be very useful in a second. So at these conditions, if the only work done is caused by expansion or contraction, then the heat flow and the enthalpy change for the process are equal. And this makes enthalpy the most convenient choice for determining heat, just because it's the normal condition that you carry out reactions, constant pressure. So in order to clearly communicate the energy transferred during a chemical reaction, we write the equation as a thermochemical equation. So in a thermochemical equation, the enthalpy change of the reaction is written to the right of the balanced equation. So you have this example. And the important thing is you notice I don't say the delta H for what quantity of this reaction. So however you balance the equation, the delta H goes with that. So when you look at this thermochemical equation, it means that 286 kilojoules of heat is released from the reaction when 1 mole of hydrogen gas reacts with 1/2 mole of O2 gas to make 1 mole of water. So if the direction of the chemical equation is reversed, the arithmetic sign of delta H is also reversed. So if the reaction goes one way and heat's released, that means if you have the reaction go the other way, that same amount of heat would have to be put in. So that shows us that at the bottom here, if the reaction of hydrogen and oxygen is exothermic, the reaction to make hydrogen and oxygen is endothermic. So you just would change the sign. And then we want to think about the coefficients as we go through this process. So we know that the quantity of a reaction is going to determine how much heat's released or absorbed. So if in the first balanced thermochemical equation, it's 1 mole with 1/2 mole, and it releases 286, if I just balance that equation by multiplying it by 2, then I'm going to get twice as much heat release. So I'm going to have to multiply 286 by 2. And so I'll have 572 kilojoules released if I've just changed how I balance that chemical reaction. Same thing if I were to multiply it by 1/2. So however you balance the equation is going to determine the quantity of heat. And so if you start out with 1, change it to 2, you're going to multiply by 2. But if you start out with 1 and change it to 1/2 for the hydrogen, you're going to have to multiply by 1/2. So the delta H of a reaction depends on the physical state of the reactants and products. So that's crucial. So it would be a different amount of heat, for example, if I said the reaction of hydrogen gas with oxygen gas to make water in the gaseous phase. That would have a less negative delta H, because some of this negative delta H comes from that water condensing. So this shows you in the second example, if the water was gaseous, you get slightly less energy. It's slightly less negative. So the phase is important because phase transitions involve heat transfers. So this is an example. Gummy bear contains some sucrose. And when the gummy bear reacts with potassium chlorate, 43.7 kilojoules of heat is produced. So we want to write a thermochemical equation for the reaction of 1 mole of sucrose. So we want to put the delta H next to this reaction. So we're going to start out and we're going to convert the grams of sucrose in that gummy bear into moles of sucrose. And then we're going to do the same thing for the potassium chlorate, change its mass into the moles. And then we're going to try to decide what's the limiting reactant. So in this equation, it reacts 1 mole of sucrose with 8 moles of potassium chlorate. So which of the reactants is limiting? So one way to do that would be to say, what's the ratio of potassium chlorate in the sample I've reacting so what's the ratio of potassium chlorate to sucrose in the reaction mixer I've created compared to the stoichiometric ratio? So the ratio should be 8, but it's 7.52. So that means I don't have enough potassium chlorate to react all of my sucrose. So the potassium chlorate is our limiting reactant. So the balanced equation indicates 8 moles would be required for 1. And because that's less than the stoichiometric ratio, the amount I put in, that means that the limiting reactant can be used, and that's the moles of potassium chlorate. So that tells me if I take the heat that was released, the 43.7, so if it's released, it's negative 43.7. And if I divide by the moles of the potassium chlorate that could react, then I end up with 744 kilojoules per mole of potassium chlorate. Why did they put it as positive? Should be written as negative. Maybe they'll do that on the next slide. So it's still negative because that reaction gave off that energy. So because the equation as written is 8 moles of potassium chlorate, that means I have to take the per mole of potassium chlorate and multiply it by 8. And now I have 5,960 kilojoules if this reaction took place as a 1 mole of sucrose to 8 moles of potassium chlorate to make 12 moles of carbon dioxide and 11 moles of liquid water. So they should have that written as negative. So if you were then to complete that, yeah, they don't complete it. If you were to complete the thermochemical equation, you'd put negative 5,960 kilojoules next to this reaction as the delta H. So enthalpy changes are typically tabulated for reactions in which both reactant and product are in the same conditions. And we usually call those the standard state. So if you go to a table, you need to know what conditions, so you know something about the quantities. So a standard state is a commonly accepted set of conditions used as a reference point for the determination of properties under different conditions. So for us, our standard state is going to be the bar. And if we have a solution, it will be molarity. So in a reaction, if we have gases, they're going to be at a pressure of 1 bar. And if we have solutions, they're going to be at a concentration of 1 molar. So we're going to include a little, I call it a knot, the little 0 here in an enthalpy change if we're talking about standard conditions. The temperature isn't necessarily part of it, but when you go to a table, you're going to be given a delta H at a particular temperature. So our temperature will be 25 degrees, which is 298.15 Kelvin. And so this symbol, they must somehow, this D right here should be a delta. So the symbol delta H with that little knot sign indicates it's the enthalpy change for a process under these standard state conditions of 1 bar pressure and 298 Kelvin. So that D right there should be a delta sign. So the enthalpy change for many types of reactions are available in the literature. And recall that delta H is an extensive property, so it's proportional to the amount of substance involved. And it's usually normalized to a per mole basis when you get it out of a table, which will make sense out of that. So, for example, if we're talking about the standard enthalpy of combustion, it would be a delta H with the little knot sign C for combustion. And that would be the enthalpy change when exactly 1 mole of substance burns in an excess of water or an excess of oxygen, sorry, under standard conditions. And so that's the heat of combustion. So the enthalpy of combustion of ethanol is negative 1,366.8 kilojoules per mole. And so if you were to write it as a thermochemical equation, sometimes their delta works and sometimes it comes out as a D. So I don't know why that's happening to them, but the thermochemical equation would have the reaction written out for 1 mole of ethanol. So in this case, it's liquid ethanol, which is the phase for ethanol at room temperature. They should also include the phase of CO2, which would be a gas, which they left off. And then the D, once again, should be a delta. So these are just the standard enthalpies of combustions for a few different molecules. Notice hydrogen has a large one. And if you actually convert it to per gram, because hydrogen's so light, it's the largest delta H of combustion of any chemical reaction is for hydrogen gas. This is gasoline exploding. It's very exothermic, but the explosion is just the combustion reaction of gasoline, which usually takes place in a much slower controlled way in your car. But under the right conditions, it can all burn at once and have an explosion. So as that figure suggests, gasoline is highly exothermic when it burns. So if we determine the approximate amount of heat released by burning 1 liter of gasoline, assuming the enthalpy of combustion of gasoline is the same as that as isooctane, a common component of gasoline, and it gives us the density of isooctane. So when you talk about gasoline, it's not a standard composition. Different gas stations would have different mixtures of hydrocarbons. On average, they're about 8 carbons long, which makes them an octane, and isooctane's kind of the average. So we'll use that, even though that's not the only thing in gasoline. So we start out with the 1 liter of the isooctane. We convert that into grams with the density. Then we convert that into moles with the molar mass. And then we look at the value for the delta H is negative 5,460 per mole. And we end up with negative 3.31 times 10 to the 4th kilojoules of energy would be released when that 1 liter of isooctane burns. these are some pictures, and there's a discussion in your book about how you can make fuels from plant material so that they're not contributing to an increase in CO2. So if you burn gasoline, you're clearly taking it out of storage, which for millions of years it's been underground. You're burning it and you're increasing the CO2. But if you have algae, which are using CO2 to make oils that can be burned, then you're not changing the CO2 overall right now, because the algae growth process involves taking CO2 out. So there's a discussion in your book about how algae, which doesn't take a lot of area to grow, can be used to make oils, which can then be used to make biodiesel. So there's a type of reaction that's commonly put into tables, and then we'll see how we can use those. It's called a formation reaction. And so the standard enthalpy of formation is an enthalpy change for a reaction of exactly 1 mole of a substance when it's produced from the elements in their stable states under your standard conditions. So if we look down here, if we say the delta H of formation, standard state for CO2 gas is negative 393.5. That means that it's start with the elements in their stable states. So if you found carbon at 25 degrees in 1 bar, it would be solid. And if you found oxygen, it would be the diatomic oxygen molecule in the gaseous phase. And if we're making CO2 gas, this delta H that I got out of the table is the delta H for this reaction. So it's a formation reaction. And so 393.5 kilojoules would be released when 1 mole of CO2 is produced. So by definition, the standard enthalpy of formation of an element in its most stable state is equal to 0 under standard conditions, because that would say the standard enthalpy of formation of some element, let's say carbon, would be make carbon solid out of what it is when it's in its stable state, and that's carbon solid. So carbon solid going to carbon solid would have no change, and therefore the delta H of formation for carbon solid would be 0. So write the heat of formation reaction for each of these. Yeah, so we can just look at these. So if we take carbon and graphite's actually the more stable state. You can also find diamond in your tables, but graphite's the more stable state, solid graphite. So we're going to take, in order to make ethanol, which is this A right here, we're going to take carbon, hydrogen, and oxygen, because those are the elements. Their stable states are solid graphite, gaseous diatomic hydrogen, and gaseous diatomic oxygen to make the C2H5OH liquid. So you can do the same exact thing for the second reaction to make calcium phosphate. So you're going to make a mole of calcium phosphate from calcium, phosphorus, and oxygen in their stable states. And so Hess's law allows us to combine different paths from reactants to products. So Hess's law reminds us that enthalpy is a state function. So if you're going from here to here in some chemical reaction, if you can find another path, maybe a 2 or 3 step path where you carry out several reactions, but overall you still get from the same reactant to the same products, then the delta H's will be the same, because enthalpy doesn't care about path. So there are 2 ways to determine the amount of heat involved in a chemical change. You can measure it, or you can calculate it using Hess's law from other experimentally determined enthalpy changes. So some reactions are difficult, if not impossible, to investigate with measurements. And so Hess's law makes it possible for us to combine known values. So Hess's law. So if a process can be written as the sum of several stepwise processes, this is just what I said, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. So that's equivalent to saying 1 step from reactants to products, 10 steps from reactants to products. If the overall change is the same, those steps, whether there's 1 or several, have to add up to the same delta H. So Hess's law is valid because enthalpy is a state function, and enthalpy changes depend only on where a chemical process starts and ends, but not on the path. So that's what we discussed in previous slides. So if we have this reaction of carbon solid plus diatomic oxygen going to CO2 gas, and it has a negative 394 kilojoule delta H. We can look at another way to carry that out. We could take the carbon, react it with just enough oxygen to make carbon monoxide. We could then take the carbon monoxide, react it with more oxygen to make CO2. When you add those two reactions together, you notice that the carbon monoxide cancels from both sides. So there's no net change in carbon monoxide with these two steps. And the 1/2 O2 adds with the 1/2 O2 to make 1 O2. And so these two steps are equivalent to this reaction. And so if we add those two steps together, we should get the same negative 394. And yes, indeed, we do. So those two steps are equivalent to the overall reaction I'm looking at. So we know that the delta H sum for those two steps has to equal the delta H for doing it in one step. And this just shows that in a visual. You could do it as a one-step reaction or a two. Those arrows on the right have to add up to be the same length as the arrow on the left because the enthalpy change is the same whether it's done in one step or two. So we also can use Hess's law to determine the enthalpy change of any reaction if the corresponding enthalpies of formation of reactants and products are available. So we will see that the decomposition of the reactants into their components, that's the negative reaction of an enthalpy of formation. So if you take all the reactants and take them back to the elements in their stable states, that step would have negative delta H of formation for reactants. But then you can take, in the second step, take those reactants onto products, and that would be the positive delta H for that of the products. And so their symbols are all messed up in this one. So the standard enthalpy change of the overall reaction, therefore, is equal to the sum of the enthalpy changes of formation of the products minus the sum of the enthalpy change of formation of reactions. So I can just tell you that what this really should say is delta H standard state reaction on the left-hand side, and that A with the hat on it should really just be a sum, where it says with the summation representing the sum of. So I'll rewrite this in class for you, but all it's doing is putting into words the top sentences. So it's a sum of all the delta H's of formation of products minus a sum of all the delta H of formation of reactants. And how do you use that? If we want to know the delta H for this reaction of nitrogen dioxide with water to make nitric acid and nitrogen monoxide, we look up in a table and we get for the product in the table, it's negative 207.4 kilojoules per mole for the nitric acid, but I have 2 of those moles in my reaction, so times 2, plus we have 1 mole of nitric monoxide gas. And out of a table, we found that its delta H of formation is 90.2. So there's only 1 mole. And then I'm going to subtract what I get out of the table for the reactants, each of the numbers multiplied by the stoichiometric coefficient. So this delta H for this reaction should be negative 138.4 kilojoules. So I don't have to go into the lab and measure that because I already have measured values that I can relate together through Hess's law. And the last thing we're going to think about is the strength of bonds and how it relates to a delta H. So we're going to skip the section on the Bohren-Haber cycle just because we're also going to skip some sections on ionic bonding. Just is a bit too much to do all of it. Not that it isn't important, but covalent bonds are more important if you're talking about fossil fuel reactions. So we're going to use average covalent bond energies to estimate enthalpies of reactions. So we're going to skip the Bohren-Haber cycle, which involves the energies of ionic compounds. So if we have this reaction, we could look up in a table and it could give us the average energy it takes to break a carbon-hydrogen bond. And so in this process, we have to break 4 carbon-hydrogen bonds. So this delta H would be 4 times the heat of dissociation of a carbon-hydrogen bond. So the important thing in these examples is you have to know the bonding. So we have to go back and understand our Lewis structures. So we have to know if we want to react carbon monoxide with hydrogen to make methanol, which is what this reaction is, we have to know that the carbon monoxide has a triple bond because it will have a different bond energy in a table. And that when I form the methanol, each of those is a single bond. So these are a bunch of examples that we'll work out in class, but the important thing is you need to understand the structure in order to know what the bond energies are. And this is the Born-Haber part that we're going to skip. And we will look at a lot of these reactions, and we'll use these, especially for combustion reactions, to think about why it is that we say energy stored in the chemical bonds of fossil fuels. It's really because when you break the bonds in a fossil fuel, carbon, hydrogen, carbon, carbon, but form the bonds in CO2, CO2 is a super stable bond, so you get a lot of energy back. So it's really not that the energy is stored in the bond, it's that when you change the bonding from carbon, hydrogen, and carbon, carbon, you make it into a much more stable bonding system, carbon and oxygen. And that's really why that energy difference is used to release that stored energy. So that is all for that chapter. We have one chapter left. Okay.